Equivalent systems. So two systems of equations involving the same variables, right, are said to be equivalent if they have the same solution set. That means if you look at the two systems, they could look different, but if they share the same solution set, that means they are equivalent. So there are three operations that you can use in order to obtain an equivalent system from an original system. The first operation is you can interchange any two equations, interchange the order of any two equations in the linear system. Let's say, for example, if I look at the same, this 2 by 2 linear system, okay, 2. And then if I interchange the two equations, so I say this is equation 1, equation 2, and I just switch the order. This is equation 2, equation 1, switch the order to 2x1 minus x2 equals 2, and then x1 plus x2 equals to 1. This system here, the new system, after I interchange the order of the first and the second equations, these two systems here share the same solution set. All right. And then the second operations is you can multiply, one equation can be multiplied by the same non-zero number, okay? Both sides of an equation, you take the whole equation, both sides, and multiply both sides of an equation by the same non-zero number. For example, I still use the same system as above here. And if I multiply the first equations, both sides of the first equation by 2, which is, I say, first equations, right? And you multiply it by 2. So this is the first equations, this is the second equations here. And what I get, so the new equation will be 2 times, I multiply 2 here, right? And 2 here. So yeah, 2x1 plus 2x2 equals to 2. Okay. And then I will have, and I keep the second equation as the same. So it would be just 2x1 minus x2 equals to 2. As you say, this is the new equations after I take the first equation and multiply by 2. And again, this two equation here will share the same solution set. That means if you find a solution for this system, that solution will also be the solution for the system. All right. And then the last operation is you can multiply one equation, and a multiply of one equation may be added to or subtract from another. What does that mean? That means, again, if I have the same equations, same system, say 1 and 2, and I multiply the first equations, right, by 2, and then first I take the second equations. See, maybe add or subtract from another. So let's say I take the second equations and I subtract 2 times the first equation. What does that mean? That means first I multiply the first equation by 2, and then I take the second equation and I subtract the first equations. Let's see what it means. If so this is one operations, right? And this operation is a combination of maybe 2 operations. Maybe I multiply the first equation by 2 first, and then now I use this, and now I can take the second equation and I subtract the new first equations, okay? But if I combine the 2 operations at the same time, I can just do that. So the result of this operation will be 2x1 minus 2x1 will be 0x1. Negative x2 minus 2x2 will be negative 3x2. And I have 2 minus 2, I'll get 0. Okay, so this is the result of this operation here. Okay, so 2x2 minus 2x1 is 0x1. Negative x2 minus 2x2 is negative x2. And 2 minus 2 times 1, which is 2 minus 2, is 0. And this is the second equation, the new second equation after these operations. And the first equation still stay the same, which is x1 plus x2 equals to 1. All right. Again, I obtain an equivalent system to the original system by applying the third operation. So this is the third operations. You multiply a constant, right, a non-zero constant to an equation, and you subtract or add that equation to or with another one. All right. So this will, these three operations here will help you solve for the system, right? You get the same solutions. That means once you obtain an equivalent system, and then if you solve for the system, right, and solve this system and get the solution, so the solution for the new system here will be the same as the solution for the original system. Is that right? So let's look at this system here. You will get what? So x2 equals to 0. And from this equation, x1 equals to 1. So this is the solutions for this equivalent system. And also, this is the solutions for this original system. All right. So the idea of obtaining equivalent system is to solve the original system in an easier way. So let's imagine so let's say that you want to solve for the system, right? And it's kind of, you kind of stuck here. But after you apply the third operations to the system this way, then you obtain a new system. And this system here is much easier to solve because if you look at the second equation here, you know right away x2 equals to 0. And from the first equation, you can solve for x1. So you can obtain the solutions for the this equivalent system much easier compared to obtaining the solution for the original system. So the idea is you applying operations onto a system to obtain equivalent systems, which is much easier to solve. All right. And well, the next thing is we want to talk about the strict triangular form. So the definitions of strict triangular form is a system of linear equations whose coefficients might appear as a triangle, right? So this is a triangle here. When you see that all the coefficients in this triangle are non-zero, all the coefficients outside of this triangle is 0, are zeros. And this is an example of a strict triangular form of a system. And by definitions, the strict triangular form, if a system will be in a strict triangular form if the kth equations, in the k equations, the first, second, third equation, the coefficients of the first k minus 1 variables are 0. And the coefficients of xk is non-zero. What does that mean? That means if you look at the first equations, right? All the coefficients of the 0 equation will be 0. But because it's the first equation, you don't have any equation that is before this first equations. So that's true that all the 0 the coefficients of the zero equation is 0 because it doesn't exist. And also the coefficients of x1, coefficients of x1 is not 0. Yes, it is 2, so it's not 0 because we look at the first equation. How about the second equations? If you look at the second equations, then you need to make sure that k minus 1, the coefficients of the k minus 1 variables are 0. So k minus 1, when k equals to 1 and when k equals to 2, then the coefficients of x1 should be 0. Yes. Coefficients of x1 is 0. And the coefficients of x2 should be non-zero, which is -1, so that works, right? And again, if you look at the third equation when k equals to 3, then the coefficients of x1 and x2 should be 0. And the coefficients of x3 is not 0. Okay, so if your system satisfies all of these conditions, then your system is in strict triangular form. Now, why do we want to look at a strict triangular form? It is because if you look at the strict triangular form, you can solve your system easily. For example, so if I look at this system, and which is already in the strict triangular form, right? Can you solve the system? Yes, I can. I look at the third equations. So the first, since the first variable and the second variable are 0, right? Then I just have in my third equation, I only have one variable, x3, and I can solve for x3 equals to 3. I know it right away. Is that right? So if I solve for x3, then I can look at the second equations. I have x3 equals to 3, then I can solve for x2. So x2 equals to 2x3 minus 2, which is 2 times 3 minus 2, which is 7. All right. And once I have x2 and x3, I can look at the first equation to solve for x1. x1 equals to 1 minus 3x3 minus x2 divided by 2. And 1 minus 3, x3 is 3 minus x2 is 7 divided by 2. And I would have it 1 minus 9 is -8, -15 over 2. So this is my solution. So looking at this system here, it looks a little complicated, but actually because it's in the strict triangular form, I can solve this system using a method. It's called backward solving. Backward, like you solve this system backward. That means you start with the lowest equation, the third equations, and you move to the second equation, and you finish the system solutions at the first equation. You're solving this system backward. Oh, this one, sorry, this should be 6, right? And then you have 6 here. And then you have oh, well, 2 times 3 is 6. 6 since this is 4, and you should have 4 here. And then you should have 9, 1 minute 9, -8, -8, minus 4, negative 12 is going to be negative 6. Yeah, okay. All right, so this is the solutions, right, for the system. And then when I want to draw, when I want to present the solution set for the system, it's going to be an 3 tuple, which the first value should be the value of x1, which is negative 6. The second value should be x2, which is 4. The third value should be 3. So this is my solution set for this system. And you can see how easy it is to get the solution set when your system is in the strict triangular form. So let's do an example here. You have a system, right? 3 equation with 3 variable, x1, x2, x3. You want to transform it into a strict triangular form, if possible, and then you're trying to solve for the system, right? So for strict triangular form, first you look at the first equations. The coefficients of the first variable is non-zero, so you can just keep the first equation like that, right? And then you know that, okay, if you go to the second equations, this here has to be 0. This coefficients of the first variable in the second equation has to be 0. And if you look at the third equation, you know that this coefficients and this coefficients here have to be 0, right, in order to satisfy, in order to fit the system into a strict triangular form. Okay, how can I force this coefficient to be 0? I can use one of the operations. What operation I can use? So in order to make this 0, I can use this first equations. So the first operations is, I'll take the first equation. Let's see, this is the first equation, second equation, and third equation, okay? So so I have a plan, right? I keep the first equation, which is 3x1 plus 2x2 plus x3 equals to 0. And I need to transform the second equations. So my first operations is I take the first equations. I subtract, so 3 and negative 2. Then I can, well, think about it. So I just want this to, right, to be 0. So, and I want this to be 0. Then maybe one thing I can do is I can add the equation 2 and 3 together. Let's do that. So I take equation number 2 plus equation number 3, okay, to get my new equations here. So 2 and 3, I get negative 2x1 plus 2x1, 0x1. Well, I achieved my goal. X2 plus x2 equals to 0x2 is another result from this operation here. And negative x3 plus 2x3 is 1x3. And 2 plus negative 1 equals to 1. Okay. And I still have, so that's the second equations. I still keep the third equation as is. So this is my first operations. I achieved the goal, and actually I have 2 zeros here. So if I have 2 zeros here, it makes more sense for me to squish the order of the second and the third, because my goal is to have 2 0 in the front on the third equation. So I switch 2 and I switch, right, to 3. If I switch it, then that means I still keep the first equations as it is. I switch the 3 here. And the third equation will be this one. What does it mean? That means my third equation is in the correct form. I don't have to worry about it. Now I just need to worry about the second equations here. For the second equations, I need to apply an operation so I can get rid of this term. I can force this term equals to 0. at this point, go 1, 2, 3, right? At this point, I use the third operation, which is I take the first equations. Okay, either is I take the first equations, I subtract 3/2 of the second equation, because I know that in my mind, I know that well, 3 here, right? 3 minus 3/2 times 2, right? So 3 is this coefficient here, and 2 is this coefficient, and 3/2 here is the constant that I want to multiply to 2. So then when I take 3 minus 3/2 times 2, I got 0. So 3 minus 3 is 0. So this is the right operation that I want to do. All right. So if I apply this operation onto the second equation and I replace the second equations by the result of this operations, what will I get? The first equation still be the same, right? Not gonna do anything with the first equation because it's in the correct form. The second equation will be, I'm pretty sure that the first coefficient will be 0, x1, because that's what I did. And then the second one will be 2, right? It's 2 minus 3/2 minus 1. So the second one will be 2 minus 3/2 times 1, right? So which you have 2 minus 3/2, which is 4/2, it's just 1/2. x2. Does that make sense? So that's how I calculate the second coefficients for the second variable. And for the third one, I just take 1 minus 3/2 times 2. And I will get 1 minus 6 minus 3 is just going to negative 2 x3. Okay. And now I remember that I did something wrong for the second one here. So for the second, let's do it again. For the second variable, x2, I have 2 minus 3/2, but then it's just negative 1. So I should have 2 plus 3/2. So that would be 7/2. 4 plus 3 is 7/2. So I should have 7/2 x2 instead of 1/2 x2. Okay, so keep in mind and pay attention to the sign in front of each of the coefficients. And then for the constants, I would have 0 minus 3/2 times negative 1, which is plus 3/2. So equals to 3/2. Okay, and then again I have, and I'm finished the second new equations when you apply these operations. So to take the first equations minus 3/2 of the second equation, because again the goal is I want to force these coefficients to be 0. And you have 3 here, right? And minus 3/2 times 2, you will get 3 minus 3 is 0. And then you have to use these operations, apply these operations on to each of the variable, x2, x3, and the constant. And at last, you will come up with a straight triangular form of this system. The system now, if you want to draw a triangle here, it looks like a triangle, right? Okay, I have 0 here. And now you can use backward substitutions to solve for the system. So the system will be x3 equals to 1. 72, and then if you solve for x2, you will get, and you're using the second equation to solve for x2. So 77 over 2x2 equals to 3 over 2 plus 2 times x3, which is 3 over 2 plus 2 times 1, which is 2 over 2 plus 4 over 2 is 7 over 2. That means x2 equals to 1. How about x1? Now you know x2 and x3, you can use the first equation to solve for x1. So look at the first equations. 3x1, right, equals to 0 minus x3 minus 2x2. So 0 minus x3 is 1, minus 2x2 is 1, so you will get -3. That means x1 equals to -1. All right, so combine all this together, you will have a solution set. You achieving to the solution set for the system, which is x1 is -1, x2 is 1, and x3 is 1. This system has only have a unique solutions, and the solution for the system is a 3-tuple -1, 1, and 1. All right, this is an example of how you can use system operations, the 3 system operations, to transform a system, right, into a triangular form, a strict triangular form. And then from the strict triangular form, you can use a backward substitution in order to solve for the solution set.